So I talk about dimers and rail yard graphs, but before I do that, I'll talk about something that's a bit less general, that's more like historical in the way we got to those dimers, and that are steep tilings. Okay? So the steep tilings part is joint work with Jérémy Boutier and Guillaume Chapuis, and the follow-up is with the same team, but with two extra boys, Cédric Boutillier and Sanjay Ramasamy. So before I go to these general objects, I'm going to try to give you a warm-up on how we got to those objects. So my talk will be in three parts. Okay, you already know two of them. And the first part is going to be about the Aztec diamond, the tilings of the Aztec diamond, and the pyramid part. So let's start slowly. So what's the Aztec diamond? So that appeared about 20 years ago. So it's shaped like a diamond. Okay. It's like 4 staircases that are glued together. And the size of the Aztec diamond is the number of corners you can read on one of the sides. Okay? So that's the Aztec diamond of size 1, size 2, size 3, and size 6. Okay? And what you want to tile, you want to tile this region with dominoes. So here are the 2 domino tilings of the Aztec diamond of size 1, and here are the 8 domino tilings of the Aztec diamond of size 2. So that's nothing. So let me recall, we have dominoes, so 1 times 2 rectangle. We have the Aztec diamond of size 4. It's always tileable. I can put all horizontal tiles and tile the region. Okay. And I can do flips. So for example, if I have a square with 2 horizontal tiles, I can change them to 2 vertical tiles. I can do some flips on this Aztec diamond. So for example, here, I can flip over things, etc. Okay. And so the theorem is the following. So the number of tilings of the Aztec diamond of size L is 2 times L plus 1 over 2. Okay. And if I start with the Aztec diamond with all horizontal tiles and apply this flip operation, I can get to all the tilings of the Aztec diamond. Okay. So here, if I perform 1 flip, I can go to these 2 tilings. If I do 2 flips, I can go to that one. 3 flips, I go to that one. 4 flips, I can go to those 2 tilings, and 5 flips at the end, I arrive to the tiling with all vertical tiles. So there's another way that we see how to see those tilings, is to see them also as pile of bricks. So I won't give very detailed here, but this is related to height functions given by Thurston. And here is a tiling of the Aztec diamond in the brick version. And you can see, if you think of it, that the flip operation is the same as removing or adding a brick in your pile of bricks. Okay, let's see a 1-minute proof of how to count the number of tilings of the Aztec diamond. Okay, that's a little advertisement for quite quick enumeration. So as you've seen on my first slide, there are 4 types of dominoes. Okay, depending on the parity of the corner of the top left of my domino. So I'm going to do a bijection between tilings of the Aztec diamond and non-intersecting paths. And so what I do is for one type of vertical tiles, I put an up step. For the other type, I put a down step. And for my 2 horizontal tiles, I put all horizontal step or nothing. So when I apply this, I get a bijection between my tiling and non-intersecting path using those 3 kinds of steps, where the starting paths are here and the arrival paths are here. Okay. And we all know, using the Lindström-Gesell-Dienno methodology,
Sorry, as chair, I'd ask you to leave your comments until the end.
Christian would know how to say it, but maybe Peter will be better. Anyway, if you want to count, so that should be an error here, sorry. The number of tilings, it's going to be a determinant. I write it like that, my determinant is disgusting, and I don't know how to compute it. But here is a combinatorial trick. I change my arrival, my departure and arrival points here. So the number of non-intersecting paths is the same, because here I'm forced to go up to be non-intersecting. Okay, I still have the same number of non-intersecting paths, but in my determinant I have different numbers. But that determinant is easy to compute. Okay. So why is it easy to compute? Because what I have here, I guess this should be off. What I have here is big Schroeder numbers. Okay. And what we know is that big and small Schroeder numbers differ by a factor of 2. And what are the small Schroeder numbers? They are the same path, except we can't have an horizontal step at height 0. Okay? That forces in the non-intersecting path that the small path here is up and down. And that fixes you all those things here. This will all have to be up steps there. And so what you look is finally the determinant of the small Schroeder number is the number of Aztec diamond, the tiling of the Aztec diamond of one size less, AL minus 1. Okay? I know that all my entries differ by 2, and so I get the number of tilings of the Aztec diamond is 2 to the n plus 1. So that's a proof of one slide, but I use overproof that. But what I'm interested in today, as I said before, is my flip operation, and I want to count tilings according to the number of flips you can do. Okay? So here, I can Q to the minimal number of tilings you have to do to go from the horizontal, the tilings with all horizontal tiles to a given tiling. And again, it's a very nice result. It's a product from I equal 1 to L, 1 plus Q to the 2i minus 1 over L minus 1 plus 2. Okay. We can see the example here again. So that's Q to the 0, that's our starting tiling. Q to the 1, Q to the 2, etc. And I can factor this polynomial and get 1 plus Q to the square times 1 plus Q to the 4. Okay? And you can get something a bit more refined. You can count flips on a given diagonal. And again, you have that very nice product, 1 plus Q to the 2i minus 1 to 1 Q to the 2j minus 1. You can see again in this example here. So here we flip on diagonal 1, diagonal 3, diagonal 1 and 3, 1, 2, 3, etc. And this again factors very nicely. Okay, now we know how to count these tilings. And that's a very nice way to also randomly generate them. So that's again in that starting paper. And that's called the shuffling algorithm. So it's a very small, very easy and beautiful algorithm. So if I want to do a tiling of size L, from the tiling of size L minus 1 and L bits, okay? There's a notion of active cell. So a cell is active if the up left square is white, if L is even, and gray, L is odd. And here is the algorithm. We look at the active cell. If a cell has 2 dominoes, we erase it. If a cell has 1 domino, we move it to the other side. And if a cell has no domino, we flip a coin. Okay. So 2 dominoes, I read A, erase. 1 domino, I push it to the other side. And if I have no dominoes, I flip a coin. Okay. And the beautiful thing is when you start by an Aztec diamond of size L minus 1 and you do that, you're going to flip exactly L coins. So here is the example for L equals 3. So I'm going to move that one, those two, and those two. And I have 3 places where I flip for L equals 3. Let me show you a movie of what that did. You see the domino of the Aztec diamond growing. Okay. So that's a random Aztec diamond that's of size 100 at the end. And what you see on this picture is that it doesn't look so random. Okay. And so there are some very nice
Control L.
There's some very nice result on how, when L goes to infinity, a random tiling looks like. Okay, it's called the artist circle theorem. So there's a prescribed circle. And when you look at what's around, it's all frozen. Okay. There's way more non-data things about the fluctuations around the boundary here. And very recently, there was the computation of the correlation kernel. Okay, that gives you very precise things. And we'll see a way to really write that correlation kernel in a more general way.
I mean, people knew the kernel like way before us. But I mean, for the general. Yeah.
So the inverse of the setting there. So let me go to my second part of the introduction. So these are pyramid partitions. So that was done by Jérémy Boutier. So what is a pyramid partition? So it's going to be an infinite object. Here we have just a finite part of it. But here you have one square, under it 2, then 4, then 6. So at even level you have n by n plateau, and at all levels n by n plus 1 plateau. Okay? And what you want to count is the number of configurations you obtain after taking off n bricks. Okay? So of course now it's infinite. We don't have just a finite region.
2 by 2 by 2 by 2 bricks? Or
yeah. So that's one brick here. One brick is 2 dominos. Okay, so when we start with the full, we have one way. When we take off the first one, we have just one way because we take off bricks only from the top, bricks that are maximal. If I take off 2 bricks, I can take off this one and this one, or this one and this one. And if I take off 3 bricks, I have 5 ways to do it. Okay? But you can try, and if you take off 4 bricks, that's not the Catalan, it's 12. So let me set you up. So we start with that minimal pyramid, and we take off some bricks. But if we look at that pyramid from the top, it's back to a tiling problem. Okay? But this time it's domino tilings of the whole plane. So my starting, my minimum tiling is this one, so that's my maximum brick here. And AN is this time the number of tilings we can get after n flips. So this was conjectured by Kenyon, the form of the generating function of the AN. Let me show you what it is. So it's a result of Ben Young, who is here. So if I want to compute the generating function Q to the number of flips, it's a very nice product again. Product from I greater or equal to 1. 1 plus Q to the 2i minus 1 to the 2i minus 1 over 1 minus Q to the 2i plus 1. And the limit shape of this object is an amoeba of a polynomial, and it was also computed actually way before the generating function, 3 years before. So again, these objects are a bit the same. Okay? They have nice limit shapes, nice generating functions, and so what we decided to work on is try to put these 2 objects that look a bit different in the same framework. Okay? So I have one that gives me a polynomial because it's a tiling of a fixed region, and I have one that gives me a series because it's a tiling of the whole plane. So let's see how to put these 2 together. So we call them stick tiling. So I read it that slide because we couldn't see with the other projector. Anyway, so we had a small region, small fixed region, or the whole plane. So now we'll do something that's neither one nor the other. We take a strip. Okay, so I take an infinite strip here that's bordered by 2 lines, y equals x and y equals x minus 2l, and I want to tile this region. So I can't tile it all the way. So the conditions, I'm going to have my 4 types of dominoes. Okay, and for reasons that you're going to see in a minute, I'm going to color them in green and orange. Okay, for each type, horizontal and vertical, there's an orange and a green. And so my tilings are going to be like this. So inside the strip, everything is covered, but on the boundary, things can be covered or not. Okay? And for now, I'm going to want to count tilings that are like that on the boundary. On the left boundary, everything is empty. Then I only see green tiles. Yeah. And on the right boundary, everything is orange and then empty. That's my condition.
This should also happen at the same place?
Sorry?
This should also happen at the same place?
No.
That's right? No.
And that middle one, why is that green in the middle of the ground?
Why not? I want to tie my regions with any tiling possible. I just don't have one tile. I have lots of tiles. So that's what I said here. At y equals x, I have no dominoes and green dominoes. And here's the definition of steep tiling. So a tiling is steep if and only if, when I look at plus infinity in that direction, I only see green dominoes. And if I look at minus infinity in this direction, I only see orange dominoes. So somehow the region where things red, orange and green are mixed is a finite region. Okay. So here is a proposition that I'm not going to prove here, but I'm giving you for things. So steep tilings, you can show that it's periodic. Okay. After a while, you're going to see a word of domino tilings that are just going to repeat. Okay. Here it's like vertical, vertical, horizontal, horizontal, vertical. And if I continue with orange tiles, I just have to repeat this period. Okay, over and over. And for the same reason, here at plus infinity, I see a word of green tiles that just repeats. And it's a period word. That's the only way when I have only green tiles to continue with green tiles at infinity. Okay, so I said that the periods are encoded by two words that are red and orange, and I'm going to mix these two words to the one word of length 2. So you'll see in a minute why I do that. Okay, so I take my green word, okay, and that's going to give me my W word at odd indices. So if I see horizontal, I put a plus, and if I see vertical, I put a minus.
What do you mean? What do you mean?
That's the odd indices of my world. Okay, 1, 3, 5, 7, and 9. I guess the arrows are not very well. So the other half of my world, I construct it with the orange world. And I do the opposite. If I see a horizontal tile, I put a minus. And if I see a vertical tile, I put a plus. And here, as I build my W world. Okay? So given that steep tiling and these periods, I get this world.
Periods you need to define.
Sorry?
Periods you need to define.
Yes.
Yeah, I fix my periods.
No, but you can, the green part, since there's more than one choice of the green thing, which you can repeat periodically.
Of course. Yes.
So that
Yeah,
they would
I could do any period.
Oh, so you just fix one and do
Yeah,
zero.
I want to count those steep tilings with a fixed period, a fixed pair of periods. But that's valid for any period. And so you can check that if you fix two periods, there's going to be a unique minimal tiling. So what's the minimal tiling? Is a tiling you build by repeating the periods. And so that on one side you have all orange and the other side all green. Okay? And you can show that all the tilings with the same periods can be obtained from these minimal tilings using flips. Okay? So here is my enumerative problem. I want to count, given a period, the number of steep tilings that I can obtain. So I can obtain an infinity, and I want to count them Q to the number of flips. So I have my unique minimal tilings, I do flips, I count them, and here is the result. Product for any word. Okay, let me tell you what that product is. And it's very simple. So I looked at pairs, I and j, where wi is plus and wj is minus. If j minus I is odd, zij is 1 plus q to the j minus I. I put it in a numerator. And if j minus I is even, I put it in the denominator. 1 minus j minus. Okay, so now you all know which word corresponds to the Aztec diamond.
All odd, then G minus.
J minus I must always be odd. Okay. So if I take plus minus, plus minus, plus minus L times, that's the word that's corresponding to the Aztec diamond. And what's that? If I build a Ferrari diagram from my word, I put a horizontal step with a plus, a down step if it's a minus, and what I have here is a hook function. Okay, that j minus I is exactly the hook of this cell. Okay, so I look at Ferrari's diagram according to their hooks. If the hook is odd, it goes in the numerator. If the hook is even, it goes in the numerator. And so as you all know, the staircase shape is the only Ferrari's diagram with only odd hooks. And so that's the only steep tiling that's going to be confined in the finite regions. All the other ones are going to be infinite. Okay, that's the only place. So let me recap. If I take the word plus minus to the L, I get back the Aztec diamond. So that's my minimal tilings here. And it's not too hard to see that with these periods that are there, I'll never be able to flip outside the Aztec diamond. So when I use the flips in that infinite strip, the only change possible is inside the Aztec diamond. Okay? And I can do the word, for example, plus to the L, minus to the L. And what I get is like the L pyramid partitions. So they are like the pyramid partitions, but when I take a strip of them, with the nice joining functions, if L goes to infinity, I get back the result for the pyramid part. And again, like for the Aztec diamond, you can follow the flips in each diagonal, and you get that same thing. Okay. So if Qi is the number of flip in diagonal I get the nice product, and the epsilon tells me whether it goes in the numerator or the denominator. Let me try to give you an idea on how you prove such a result. So it's going to be a mix of computation and bijection. So I'll just give you the bijective part. Okay. So the first bijection is very simple. You take dominoes and you're going to add particles into them. If the domino is green, you put 2 whites. If the domino is orange, you put 2 blacks. Okay. So here's the bijection. I can forget, it's a bijection. I know how to reconstruct my domino tiling from the particle. And what we see is that whenever we perform a flip, it's going to make one of the particles move. Okay? So if I do flips on the left side, it corresponds to particles who jumped on the right side. Okay? So now I take my strip, I just move it by 45 degrees, and I'm going to read each line of that sea of particles. But it can't be any set of particles, okay? The fact that I used flips, I'm going to have some strong conditions on what each line is. So here are the conditions. So I'm going to say that 2 lines are interlacing if the position of black particles are alternating. So here is an example of 2 lines that are interlacing. If I look at black, the next one on the same line, I need to have a black between them. Okay, so for example here, go there, I see a black, and okay. And 2 lines are co-interlacing. Yes, we should see a bit more here. But it's the same, but now it's the white particles that are interlacing. And if you look at that carefully, you're going to see the following. Okay? This line, particles are co-interlacing, 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 co-interlacing. But on the other one, they are interlacing. Okay? So on odd positions, they are co-interlacing. On even positions, they are interlacing. Now we all know that from particles, a sea of particles, you can construct an integer partition. So when I see a black, I do a down step. When I see a white, I do an up step. Okay. So from this sea of particles, I get a partition. So 6, 3, 3, 1, 1. Okay. And two lines are interlacing. If and only if I look at the parts of the partitions, the parts are interlacing themselves. Lambda 1 is greater or equal to mu 1, greater or equal to lambda 2, greater or equal to mu 2, etc. Okay? And they're co-interlacing if I take the conjugate of this partition. So I read the partition from the other direction here. Here it would give me 5, 3, 3, 1, 1, 1. Okay? And so they're co-interlacing if their conjugate are interlacing. So when you look at those things, that means that the two partitions here, when they're interlacing, they differ by a horizontal strip, and when they're co-interlacing, they differ by a vertical strip. So here is the result. The stiff tilings with a given period W are in bijection with sequences of partitions. So I have two L plus 1 partitions, lambda 0, lambda 1, and lambda 0. That with my border conditions, the first and the last one are empty. And then the word is going to tell me how they interlace. Okay? At even position, if W2k is plus, lambda k is going to interlace with lambda 2k minus 1. If it's minus, it's lambda 2k minus 1 that interlace with lambda 2k. And what you see is also the number of flips you need to do to get to this configuration is exactly the sum of the size of the partition. So now I transfer my tiling problem to a problem of enumeration of sequences of partitions. So here's the proof. It's true for the minimal tiling, and it stays true. Okay. So now I'll skip that part of the proof. I said that interlacing corresponds to difference of horizontal strip, co-interlacing vertical strip. And so what I'm going to use now is the super show function or the hook show function, depending on how you like to do it. I can write my generating functions as a sequence of vertex operators. These operators have nice commutation relations. I use it, and then I get my generating function. Okay. So I said that we use that using the commutation of vertex operator, but these commutations can be also done bijectively. And so what you can do with that is that you can do also some algorithms to randomly generate those objects. So if you give me a word that's going to correspond to two periods, I can choose and I can generate you any object of the stiff tiling. So here is an example for the Aztec diamond. You see the Arctic circle, and we get back also what we saw as the limit shape of the pyramid partition. Okay. So this is just purely to do experiments, but you also get some tools with the vertex operators to compute those limit shapes. So, for example, if we look at the L pyramids here, so I put the random generation, but we also know how to compute this shape. It has a really weird shape. Here you can see a cusp when L is finite. And when L goes to infinity, that cusp disappears, and you get back to this shape. So let me show you another movie, a little break, of what's going on with the Aztec diamond when Q varies. Okay? So so that's Q equals 1. Okay, so Q is going to vary from minus 1 to 1. You can see that it starts being really long, it goes to the circle, and then it goes back to really horizontal.
So what do you mean Q varies?
Q varies, yeah. The value of Q is changing. So Q equals 1, you get the Arctic circle. But for any value of Q, you take tilings are coming to Q to the number of flips.
Are these independently randomly generated for different values of Q, or is there some coupling?
Yeah, yeah.
Okay.
Yeah, it's not so fancy. so I won't detail too much that, but I said we were enumerating those tip tilings with some fixed boundary conditions, where we forced the first and the last partitions to be empty. But you can do two generalizations. So the first one, when you force the first one and the last one to be equal, that means looking at tilings on the cylinder, you get again that same generating function times another nice product. And you can also allow flips on the boundary of the tiling. So before I had forced my boundary to be frozen, now I can apply flips also on the boundary, and I get a free variate generating function, q to the number of flips, and u and v follow the size of lambda 0 and lambda 2. And again, using the formalism of the vertex operator, you can get nice product generating function. Okay. So here I have to change the qi. So the product is a bit more complicated, but of course if you set u and v to 0 in this product, you just get back to your thing, because that forces the two partitions here together. Okay, so we did domino tilings, but it's not the only family of objects that looks like that. Okay, so there are other objects that seem to have a bit the same behavior. So here is another example, so that you all know. This is plane partitions. So what are plane partitions? You can see them as a pile of cubes at the corner of a room, okay? Or you can see them as losange tilings, using 3 lozenges, okay? So it's an old result, that's nearly 1 century old, that if you compute the generating function of the plane partition, q to the number of cubes, you get again a nice infinite product. So the product from I greater or equal to 1 over 1 minus q to I to the I. Okay. Again, you can compute the limit shape of those objects, and you can also fix those objects to be inside the hexagon, and you get again an arctic circle. So those plane partitions, you can read them in rows, in diagonals here, and again you're going to get some sequences of interlacing objects, but also there's something that's really similar to what I've just told you. If I look at reverse plane partition inside a shape lambda, and if I compute that generating function q to the number of cubes, I have a hook formula. Okay? I look at all the cells of the partition, 1 over q to the hook. Okay? So it's not exactly what we had before, because here, before we had, if the hook is odd, we put it on top, if the hook is even, we put it on the bottom. Here, we just put the hooks in the bottom. So why is that? Okay? I have steep tilings and plane partitions. What you can see, what I've just shown you, is if you want to enumerate steep tilings, what you need to do is enumerate sequences of partitions that are going to sometimes differ by vertical strips and sometimes by horizontal strips. Okay? But if you look at reverse plane partition, what you do is you only add or remove horizontal strips. So I've just told you that also steep tilings are domino tilings and plane partitions are losange tilings. So how can we put them together? Okay? And we do one family of objects that's going to enumerate both plane partition and steep tilings. Okay? And so what we're going to use is dimers, because as we all know, the domino tilings are in bijection with dimers on the square lattice. So here I have 2 horizontal dimers. Okay. And losange tilings are in bijection with dimers on the honeycomb lattice. So now I get to the third part of my talk, which will be a mix of those two. It's going to be dimers on realm yard. That's a word that's a bit too hard to say. So let me first recall you what the dimer model is. Okay, you start with a graph that has edges, and a dimer configuration or dimer covering is going to be a subset of edges so that each vertex belongs to one edge. So here I have chose that those three edges here, and one can check that all the vertices of my graph are covered by one edge. Okay? That's a diamond configuration. Exactly one. Andrew told you to not say anything. Exactly one. Okay? And to each diamond configuration, I'm going to give a weight. Okay? So I put some labels on my edges. Okay? And the weight of the configuration is going to be the product of the weight of the chosen edge. So here I chose the edge R, O, and P. So now what's a real yard graph? Okay, so here is an example of a yard graph. Okay. So let me tell you. So that's how it looks. Okay. It's made of four patterns. So here are the four patterns that we call R plus, L plus, L minus, and R minus. Okay. So what are those patterns? They're all made of two sequences of white, black, white vertices. Okay. Each time we have two horizontal edges, and we have exactly one diagonal edge going from a black vertex to a white vertex. So if it's R plus, the diagonal edge is going to go up on the right part of my pattern here. If it's L plus, it's going down on the left part. If it's L minus, it's going up on the left part. And if it's R minus, it's going down on the right part. So I'm going to fix the width of my graph, but those graphs are going to be infinite in height, okay? And they're such that there's exactly one pattern in each column, okay? So that's a column of type R plus, a column of type L plus, R minus, R plus, L minus, and R minus. And they go infinitely on both sides. So the faces of my graph, the faces that are closed, can be of degree 4, of degree 8, and of degree 6. Okay? So the degrees of degree 4 are going to correspond to what I had for the square lattice, of degree 6 for the honeycomb lattice. But you can see that the degrees of the faces of degree 8 are actually 4 spaces of degree 4, because they always have vertices just of degree 2. I could contract them. So I'm going to look at dimer configurations of those graphs. Okay? So the dimer configuration is going to be such that all the vertices are covered, except some of them. So on the boundary, some things can be not covered. Okay. So I have a line here, such that under it on the left, nothing is covered, and above it, everything is covered. And on the right, everything is covered under the line, and nothing is covered above. Okay. So, and I need my steep condition now. Okay. So what's my steep condition? Is going to be that I have a finite number of diagonal edges. So if I look at infinity here, all my edges after a while are going to be horizontal. Okay? And in the bottom the same. After a while everything is horizontal. Okay. So what's the general result? The same as before. Okay. I have two words of length L. AI, that's going to tell me if I choose left or right. BI, that tells me if I choose plus or minus. AI, BI is the pattern in column I. And XI is going to follow edges of diagonal edges in column I. And the other edges have weight Y. Okay? I count my configuration with those weights. Okay, so that's my partition function. And again, I have that same product as before. So I looked at pairs I less than j, vi equals plus, bj equals minus, and I have zij. Okay. And this time, again, we have one case that goes in the numerator, the other case in the denominator. So if ai and aj are different, zij is 1 plus xij. And if ai and aj are equal, zij is 1 over 1 minus xij. So before I was interested in the flip generating function. So what I gave here is a generating function that just follows diagonal edges. But you can get back the flip generating function. So let me first tell you what's a flip in that setting. It's an example. So a flip can be on a face where half of the edges are chosen. So here I chose these 4 edges in that face of degree 4. And I just exchange the edges that were not chosen are chosen now, and the edges that were chosen are taken. So if I flip this face, I get this one. If I flip this face, I get this one. If I flip this face, so if I want to compute the generating function of this dimer covering Q to the number of flips I get, so I didn't say which was my minimal configuration, but my minimal configuration is the one with all horizontal types. Okay, I just have to set xi q to the I if vi is plus, and 1 over q to the I if vi is minus. And so again, that's a hook formula. Okay. And this setting includes everything: domino tilings, plane partition, everything. That explains why you always get those hook formulas. Let me show you the rail yard graph for the Aztec diamond. So that's this one. We take the word L plus R minus, L plus R minus, L plus R minus, L plus R minus. And that's the Aztec diamond of size 4. So you don't really see what it is. So here is the area that's going to be able to fit. So it doesn't look like an Aztec diamond because you have faces of size 8. But as I said before, those faces can be contracted. And here, something that looks a bit more like an Aztec diamond of size 4. So if you want to get back pyramid partition, you take the word L minus R minus to the air, L plus R plus to the air, and you can let L go to infinity and get back the pyramid partition. And if you want to compute the plane partitions, for example, you just take L words. So L minus to the air, L plus to the air, L goes to infinity. That gets you back those plane partition. But if you want to look at reverse plane partition in a shape, you take words with L, but you can choose any sequence of minus and plus, and you can get back that hook function. So again, proving that is using the vertex operator setting. So I won't give any detail of the proof. But let me give you a tiny bit of information on that we can get more out of that. Okay. So we can compute the generating functions, but we can also get very precise information. So before I said we were using vertex operator. Okay. So we have 4 types of vertex operators that correspond to each pattern. Have some nice commutation relation. But that's the word of bosoning operators. If you want to compute dimer correlation, now you can have to use also fermionic operators. So the creation operator and the annihilation operator. And using combinations of these operators, you can decide whether a dimer appears in your dimer configuration. So for example, if I look at that R plus pattern, this is at position K. I can test if there's a dimer here using those 2 operators. The annihilation operator followed that creation operator. Here at that position, it's a bit more complicated. You have to do a little bit of bijective combinatorics. But again, you can test whether you have a dimer here. You can use a mix of the vertex operator, annihilation, and nucleation operator. So you can put all that in your vertex operator machinery using the commutation relation and the Bix lemma, and you can compute. So let me give you an example. Here is an example of result we can get. We can compute the probability that you'll have a set of dimers in a random configuration. Okay, so I have those S dimers here given by EI. So WI is the position of the white vertex and BI of the black vertex. And this probability is a like, simple constant times the determinant of the correlating kernel. And here it looks a bit complicated. But it's just using the machinery of the vertex operator.
Okay. For an infinite region? This is for an infinite region?
No, L is fixed. So I have a word A and B, that's of line L. So the region is infinite from the height of finite. And so you can define this Fi of Z as like products that look a bit like what we had before. And the C alpha beta is just a coefficient extraction in those functions. So I don't say that it's easy to compute, but at least you can write and see it as a double control integral. And you can see that that matrix here, C alpha beta, is what's known to be the inverse of the cluster integral. So I think I'm had enough. So what I've tried to show you is that we can put these objects, like domino tilings, losange tilings, all in the same setting. So we used a lot of bijective combinatorics, but mostly the important tools is to use the fermionic and vertex operator settings to make all these computations. Okay, we can compute this generating function. If I fix a collection of dimer in my configuration, I can compute the probability that they exist. I said before that I had this condition that everything is uncovered, underlined, and then covered. But we can do the same generalization as we did for steep tilings. So we get free dimer configurations or cylindric dimer configurations. So we get again this nice product formula. And we can do lots of things like look at their limit shapes and do some random generation. We can get the whole thing. So I have a question here. And most of you must know how to answer it. So I have something that's really strict, okay? Is that my weight in each column must be the same. I put that weight xi to the diagonal edges that are in a fixed column. Okay? There should be a way to compute those where you don't force that same weight to be in each column. And what we believe is that if we understood cluster algebras and things like that, we could probably get some computations where we don't fix the weight of the edges to be the same in each column. So, thank you. There's no hook contain formula even in the hook short functions. Only if the number of variables is infinite. But here we have a finite number of variables.
So how do you deal with symmetry classes in plane partitions? Let's say the symmetric plane partitions in a box, which corresponds to the BM characters, for example. Can you get those corresponds?
But probably for very simple symmetric classes, not the fancy ones. But the ones that are symmetric with the diagonal, it's just like looking at these three pins where you can just clip on one side or something. So this is easy to get. But, the fancier symmetry classes, I would say, probably not.
So what is easy to get? That you have one edge, everything is free,
Yeah, you can fix on one edge everything to be free.
and this again have results of that kind?
Yeah, because so here you can set U or V to be 0, and that throws one boundary and let the other boundary be free. Because U follows the size of the left boundary and V follows the size of the right boundary. So if I fix one of the variables to 0, I can freeze one of the boundaries.
But you wouldn't, for the symmetric ones, you wouldn't want to freeze them, to let them be free.
Both? No? But I have to think about it. Yeah.
No, not both. On one side it should be free.
Yeah, that's what I said. If one side is free, I just put one of the variables here to 0.
So this is a formula where both sides are free?
Yeah. Here, both sides are free.
Or
If there are no further questions, thanks Sylvie again for a